groups direct ortho para, and other groups direct meta. And I also described, well, I didn't quite finish that, and there are two things that I need to do. I need to tell you why it is that the meta, I guess I've got to switch the volume up, I can switch it up quite loud. I've got to explain to you just why it is that certain groups direct meta. So let me deal with that. And the typical case is a nitro group. If you have a nitro group and you carry out an electrophilic aromatic substitution, and that's one of the intermediates. It is resonance stabilized, and I'm going to write down one. Well, I'll write them all down. I'll write down the resonance structures. And you can see that in one of these resonance structures, for substitution in the ortho position, there's a very bad situation, because what you get is a plus charge next to an atom that also bears a plus charge. And if you do this, write down the same intermediate species for para substitution, you'll see the same effect. But if you do the same thing for meta substitution, oops, that's not right. Let's see. If you write down the same intermediates for meta substitution, none of those intermediates have a plus charge on the carbon that's carrying the nitro group. And so, although the nitro group withdraws electron density from the ring and therefore deactivates the ring, the intermediates formed when you have meta substitution are less unfavorable than when you have ortho or para substitution. So consequently, if you carry out an electrophilic aromatic substitution of one of these compounds, what you get is the meta substitution product by default. The benzene ring is less activated, but attack at the meta substitution is less unfavorable. And you get exactly the same effect if instead of a nitro group with a positively charged atom directly attached to the benzene ring,
not study it, just don't do what I say.
In a case like this, where I have a doubly bonded substituent attached to the benzene ring, there's a double bond between carbon and oxygen, you can see that I can write a resonance structure in which there's a plus charge on the benzene ring. And of course I can move these electrons that way to give a plus charge here, and I can move them again to give a plus charge there. So you can see from that that a substituent of that type with C double bond O, in fact C double bond X, or even C triple bond X, substituents like that withdraw electron density from the benzene ring. And so the benzene ring is now deactivated. The question is, where on this deactivated benzene ring will an electrophile go? Well, you work out the answer in exactly the same way as I've been doing. You pretend you don't know, and you write down the intermediates for ortho attack, the intermediates for para attack, and the intermediates for meta attack. And if you do that, you'll find that the meta attack is the least disfavored. They're all disfavored, but ortho and para attack are disfavored more. So let's just write an example. Let's take this and pretend that it's going to go ortho, and so what we get is that. We can write another resonance structure. And we can write another resonance structure. In which we have a plus charge on a carbon carrying a carbonyl group. Now, a carbonyl group is polarized in that way. In other words, there's a build-up of electron density there, and so there's a deficit of electron density on the carbon. And I'm just using this little delta, which you see in calculus, to mean a small amount. So, for ortho attack, one of the resonance structures has a plus charge on carbon, carrying a carbon that's slightly electron deficient. In other words, got a plus charge on it. So just like with the nitro case, where there was a full plus charge, this is also unfavorable. And if you write down the resonance structures that the species form for para attack, you get the same situation. Of course, you can guess that if I write down the species for meta attack, I won't get that situation. And if you guess that, you guessed right. Because I can now write some more resonance structures. And I can write yet another resonance structure. And so in none of those resonance structures can you write a plus charge on one of the ring carbon atoms that carries this electron withdrawing substituent, this carbonyl. In other words, it carries this electron deficient, I'll put a little delta plus there, this electron deficient carbon. So again, once you've got one of these groups with a double bond to a heteroatom, carbon to oxygen double bond, or carbon to nitrogen double bond, or carbon to nitrogen triple bond, once you've got one of those groups there, or instead of carbon, you can have sulfur to oxygen double bond because benzene sulfur is deactivated. Once you've got one of those groups attached there, electron density is withdrawn from the ring. So the ring is deactivated. So the question is, which positions are deactivated least? And it always happens that it's the meta position. Now there's one remaining class that I didn't explain to you, and that is this very small class of fluorine, chlorine, bromine, iodine, and CH2Cl, because those things were deactivating groups, but they were still ortho-para-directing groups, unlike nitro, unlike carbonyl. And so I need to explain exactly what's going on there, because it's a little bit strange, since it's very easy to understand why electron-donating groups should activate the ring and direct ortho-para, and it's easy to understand why electron-withdrawing groups that have unsaturation, carbonyl, nitro, sulfonic acid, and all sorts of things like that, why they should deactivate the ring and direct meta. But how is it that some groups, this very small set, fluorine, chlorine, iodine, and CH2Cl, how is it that this small group can deactivate the ring and then direct ortho-para? It's not consistent with the story I've been telling you. Okay, so let's deal with, say, bromine or chlorine. What I'm going to do is I'm going to pretend that I don't know, and I'm going to write down what you get if the electrophile goes in the ortho position, then I'll write down what you get if it goes in the para position, and then I'll write down what you get if it goes in the meta position. So let's deal with ortho first. What am I doing? I want an electrifier, don't I? Generalized electrifier, and here a generalized electrifier. But now you'll notice something. Just as in the case of an oxygen substituent, I can take a lone pair of electrons from the chlorine and stabilize the plus charge on the benzene ring carbon. Because that's what I've done. I've taken this pair of electrons, moved them there, and so now I get this. So when you have a heteroatom directly attached to the benzene ring, you have that extra resonance structure. And if I do para substitution, I will see exactly the same phenomenon. So I've got 1, 2, 3, 4, 1, 2, 3, 4. In both cases I have 4 resonance structures. And in one of those resonance structures the plus charge is outside the ring. Now let's see what happens if I have meta substitution. What have I done? I moved it there, then I moved it there, and then I moved it there. So now I have 3 resonance structures. Now you remember that I said some time ago one of the rules for writing resonance structures is that the more resonance structures you can write for some species, the greater the stability that is associated with that species. So if you look at these 3 patterns on the board, the resonance structures for ortho-substitution and the resonance structures for para-substitution, and finally the resonance structures for meta-substitution, you will have to conclude that the ones for ortho and para-substitution are better stabilized by the phenomenon of resonance, because there are more resonance structures. So that tells you that it's easier, energetically easier, to form the intermediate species for ortho and para substitution compared with forming the intermediate species for meta substitution. And so on that basis, you can understand why a chlorine atom directs ortho and para. But what I haven't explained to you is why is it that it's deactivating? Well, it's deactivating because chlorine is electronegative, strongly electronegative. And there are 2 effects going on here. The electronegativity of the chlorine is sucking electron density out of the benzene ring. Consequently, the benzene ring is less willing to use its electrons to attack an electrophile. In other words, benzene ring is deactivated by this inductive effect. So it's deactivated by the inductive effect, and the ortho and para positions lead, or attack of the ortho and para positions lead to more favorable species than attack at the meta position. So you've got 2 effects here, the inductive effect, which is sucking electron density along this bond out of the benzene ring, and you've got something called the resonance or conjugation effect, which is the lone pair of the chlorine feeding electron density into the ring. And it's a balance. The outcome is a balance between the two. It turns out that as far as the reactivity of the ring is concerned, the inductive effect wins. But as far as the directing effect is concerned, the conjugation effect wins. Now, you might wonder, why is it that if I've got oxygen or nitrogen as the heteroatom on the benzene ring instead of chlorine, bromine, iodine, fluorine, or CH2Cl, why is it that in those cases, oxygen and nitrogen, the ring is activated and orthoparadirectic? Well, the reason is that the balance between the conjugation effect and the inductive effect is overwhelmed by the conjugation effect. Whereas in chlorine, it isn't always very finely balanced. So that's the story about chlorine, bromine, fluorine, and iodine, and the same thing happens for CH2Cl. You see, you all know that a CH3 group is mildly activating, and orthoparadirecting. But if you've got a chlorine atom sucking electron density that way, then this becomes mildly deactivating, but still retains its orthoparadirecting ability. Now this explanation is not 100% satisfactory, but it's the one given in all the textbooks, and so it is the one that you need to be able to reconstruct in your minds if you want to understand what's going on here. That for this small group, fluorine, chlorine, bromine, iodine, CH2Cl, there's a balance, at least for halogens, there's a balance between the inductive effect and the resonance effect. Now, in the case of the CH2Cl, there's no resonance effect. So that's the story as we are able to tell it to you at this level. And so now, there are a couple of things you should know about benzene rings. One is, if you take benzene, you carry out electrophilic aromatic substitution. Depending on which substituent you introduce, the resulting benzene ring will be activated or deactivated, and also depending on which substituent you introduce, if you carry out a second electrophilic aromatic substitution, the electrophile will go ortho, para, or meta. And you also know the arguments that one can put forward to explain what's going on. So that's enough about electrophilic aromatic substitution. I want to say something now, this is still in chapter 15, I want to say something now about reactions of the side chain of benzene compounds. In other words, benzene ring with an alkyl side chain.
No, I mean, like, where to have it. She rents it on the Oh, does she? I checked the schedule for the newer ones, and it says, like, where. I was like, oh, I didn't see that. I don't know. I'm with Taylor.
There's a lot of reactions that
Kayla, I think.
there's a lot of like sounds.
We're thinking of doing a social soon. At the meeting, they discussed what? A social, like, a event. Hopefully, though, I don't have to.
If you take methylbenzene or toluene as it's called, and you treat it with NBS and light or heat, you get the monobromination product. And all this is very, very similar to alylic bromination, and I can emphasize that if I draw if I superimpose on this picture of the benzene ring, if I superimpose some red colour, you can see that that resembles, obviously, an allyl system. It resembles propene. And the mechanism is exactly the same. And just as in the case of the allyl system, the reason why this reaction works is that this radical is resonance stabilized. I can write some resonance structures . I can write some resonance structures for it, just as I could for propylene when I remove one of the allylic hydrogens. Now these hydrogens on the toluene are given a special name. They are called benzyl. Hydrogen. Now, if you look at these other pictures that I've drawn, this clearly has two benzylic hydrogens, this has one benzylic hydrogen, and this has zero benzylic hydrogens. So if you take toluene and carry out this reaction, you will get this compound called benzyl bromide. Benzyl bromide. Now there's another reaction, which I've already written on the board. If you heat toluene with chlorine to a high enough temperature, you will get first the monochloro compound, then the dichloro compound, and finally the trichloro compound. And what's going on there is something very similar to what you had last term. I must rub that out? No? Well, it is a pretty picture, I can understand that.
Glasses look different.
Okay, what's going on here when you heat toluene with chlorine?
Sorry.
let me jack up the sound a little bit. What's going on when you do that is very similar to what you had last term for free radical halogenation of hydrocarbons. That's the first step. What this does now
I think I get it myself.
to generate another chlorine radical. And that chlorine radical comes back and attacks another benzylic hydrogen. So the mechanism is exactly the same as in free radical chlorination of hydrocarbons. You get an initiation step, which is this. You get propagation steps. The propagation step would be this one, and also this one. And then you get termination steps. 2 Cl dots give chlorine, 2 benzyl radicals that, and 1 benzyl radical plus chlorine. Here's the product. So there are 3 termination steps, 2 propagation steps, and an initiation step, and that's exactly the same as when I wrote up last term this going to RCl with heat and or light. So that's the story about free radical bromination of benzylic compounds. Now, just supposing, you have a substance like this. What you can do a free radical bromination or a free radical chlorination at the benzylic position. And the reason for that is that if the Br dot or the Cl dot removes a benzylic hydrogen, as opposed to one of the hydrogens further down the chain, what it generates is a resonance stabilized radical. And so generating a resonance stabilized radical by removing a benzylic hydrogen is a very favored situation compared with removing one of these hydrogens or that hydrogen. So this, you see, this compound, if you had to make this compound, you could first make this one either by Friedel-Crafts alkylation, or better still by Friedel-Crafts acylation and Clemmensen reduction. Then you can do a benzylic bromination or a benzylic chlorination, you get this compound. Now there are just a tell you about reactions in the side chain of benzene. But I think you don't want to hear about them today.